All right, here we are. Another great Friday. It's been a fantastic week for me. And today I want to talk to you about generative AI and how it's really risen to an incredible place in the tech space today. But more than that, not only has it risen, let's dig into the technicals a little bit and understand some of the fundamentals about generative AI because I probably haven't covered that to a great enough detail. And then I want to talk a little bit about this idea of compression, that really generative AI is doing so much more than providing us with incredible answers. It's actually driven a very semantic understanding of the world around us, and that's going to allow us to do things that we haven't really thought about. And I want to pose some interesting theoreticals about how we can apply this to the technology that we're building and perhaps even our own personal lives. So let's jump into what is the fundamentals of generative AI. And there's some discussions that I love having around generative AI. One of the best ways that I like to describe the concept of generative AI is that it is a fancy autocomplete. And the reality is that's a really great way for us to contextualize and understand the capabilities of the technology. Most everyone is familiar with the capability in the iPhone or perhaps the Android, if you will, the autocomplete. In fact, in the early days of autocomplete text messaging, we had a lot of fun with the memes, things that would get auto corrected that made no sense, or just funny changes to what we intended to send that the autocomplete feature totally changed the meaning of. Back in the old days to text messaging, we didn't even have the option to update a text message after we sent it. So we just had to laugh at ourselves and keep on going down the road. But I think that the understanding of this concept of autocomplete in terms of how generative AI works with text is really valuable because it is, to a large degree, a mechanism that is predicting the next word. Now, it's using a lot of mathematics behind the scenes to make that happen. But I think that fundamentally that is a very good description of what we're talking about. Now, let's keep going because beyond it being simply an oversized autocorrect, there is the opposite end of the spectrum, and that is that AI is incomprehensibly large when we talk about the size of these large language models. And I think large language is, in fact, a very appropriate term. We like to think that it's just so big that we can't possibly understand everything that's going on. But the reality is, when you look up at the sky and you see the universe of stars, that's not incomprehensible. It does have a semblance of order. There is meaning behind what is out there. And we have, as humans, sought ways to contextualize and understand the vastness of the universe. And so it's thinking about the large and the small that's essential to our core understanding of generative AI. Now, today, as the models have continued to evolve and change, we talked a few weeks ago about the evolution of Claude 3 and the release of their Opus model. And really, what's happened over the intervening weeks is there has been a prevailing agreement from many experts that Claude 3 Opus is performing at the level of, or better in some cases, OpenAI's GPT-4. So things are changing in 2024. Now, a portion of that could be fundamentally based upon the pure number of parameters. In fact, the CEO of Anthropic, the organization that built the Claude models, really was explaining this concept of simply scaling the number of parameters was deriving better and better results and incredible behaviors. As you know, we've talked about emergent behaviors in these models and that we're getting unexpected results from how we're able to leverage these. And I think that that is largely attributable to the way that these models are able to take in so many sources of information and turn it into useful things that it can understand and leverage for providing an answer. So as we understand the size of these, there's so much good information out there and available. I there are many folks that are putting together great information for us to understand what's going on around us. And some great sources that I have found over the years are some folks that have been very well connected to this AI universe over time. And one of them is Alan Thompson, who runs his own news information site, Life Architect. And he's provided some really good illustrations of these models to help you understand how big they are. And I'm having a little difficulty with my monitor today, so I'm going to do a little change behind the scenes here. I'm just going to keep on talking. I've been a subscriber to Alan's newsletter for a while. I've really enjoyed some of the insights that he's brought, and he's really covering things from quite a different angle. So, why reproduce some of the great information that others are putting out there? We can build on what we're learning from each other. And so in this case, I have the benefit of borrowing from Alan's illustration that helps us visualize the size of these large language models. And he's continually updating this information so we can actually see exactly how large these are in terms of their parameters. So this is a really good comparison. And I love his use of the planets to also kind of help us understand from a visual perspective the size of the ball. It pops, right? I mean, a good illustration is always a wonderful thing. So over here on the far left we have GPT-4, and that model has been estimated, and over time we've kind of gotten some better insights. That's a 1.76 trillion parameter model. And the way that I like to talk about parameters is if you've ever worked on a simple program, you can ask for your name. And what we're all used to is entering, for example, a first name and a last name. And if you turn that into a variable expression, something you can change out in a program, that is an argument, a parameter, a value that is a variable amount that you can plug in and add and take away. Some of the other models that are more well-known, we've talked about Gemini's Ultra and advanced models. This is their Gemini Ultra 1. And of course, they're up to 1.5 today. You can get access to that. They've also got the Gemini Pro model, which is smaller, reference there right next to it. The ones that we've been talking about, of course, the most are GPT-4 and Claude 3 Opus. And we've got some bigger models that are definitely in our future. There's a lot of rumors about where OpenAI is going to take GPT-5. We know that they're working actively on building the next iteration. And we also know from some recent news items that Microsoft is actually working on a much bigger program. They're actually building out an entire data center that is purpose-built solely for the purpose of training these large language models, foundational models, we usually say in the trade of AI. So it's really no telling how large the next one will be, but it's really nice to kind of see the size comparison in terms of the number of parameters that we are talking about. So if we keep going here, what I'm going to take you through is Stephen Wolfram's illustration of what is ChatGPT doing. So if you're really interested in this content, let me significantly and honestly recommend you take a look at Stephen Wolfram's blog post. He's also produced it as a book. So if you're a fan of the Amazon Kindle like I am, and you just want to have a book to carry around with you, look up Stephen Wolfram. He's also a really sharp guy. He's built some fantastic solutions over time. I've been a user of Wolfram Alpha, basically from the early days of the iPhone App Store. It was one of the first apps that I paid money for because such a fantastic capability. I always wanted to have the opportunity to carry around my TI-89 in my pocket, and Wolfram Alpha really does that for me. I don't use it all the time, but it is a very handy tool to carry around. So Stephen knows a lot about AI and how these systems come together and how they work. And He's really done a great job of helping us understand that. So let me take you through some shots that I've extracted from Stephen's discussion. And of course, I can't take credit for any of this. He put it all together, and I'm just going to share it with you because I think it's really illustrative of kind of how this thing works. So we've talked about the idea of autocomplete, but here's a good example to help you understand. If you take the sentence, the best thing about AI is its ability to, what you see here is sort of a branch illustration of what the potentials are for what the next word might be. So from a probabilistic standpoint, it's evaluating each of the terms in probability, and using that, it is able to predict the next word. Now, if you have gone into GPT for all or any of the models that you are able to do the programmable tweaks in, like for example, if you've gone to OpenAI's website and you've actually created an API key and you're able to look into the lab and play with things, you can adjust the temperature of the response that you're getting from the model. And so you take this set of words, it could be learn or predict or make or understand, or the least likely of these terms is the word do. If you turn up the temperature to increase the variation, or in some cases, the way that people talk about it is creativity, what that's actually going to do is increase the likelihood that a less likely word is going to be selected or put into the response. So if you're creating a more creative response, it's going to say the best thing about AI is its ability to do, because that is less likely. Now, on the other hand, if you're trying to derive a much more predictable answer and you don't want it to be creative, you want it to only give you information from sources that it's collected, leveraging the probability to choose the most likely word, then it's going to choose learn. And these are really important levers that we get. If you're building and designing an AI tool, your ability to actually say, no, I don't want you to be wild and crazy. I want you to be very sourced and very dependable. Then you are able to select that and dial the model's response for your need. Now, that really helps us from a simplicity standpoint, but Stephen goes a bit farther. Now, I don't want to go too deep into where we can go in terms of the use or understanding of the programming languages, but I'm trying to get myself off the screen here. You never know what's going to happen when I hit the wrong button. All right, so if you have a set of inputs and a set of outputs, what you see happening here is, from a programmable language standpoint, we're creating a list, and it's going to create a list of 7, and it's going to continue. So now it's applying the use of the model to actually fill in the next word. So this is basically taking that same sentence and we're saying, keep going and do that for the next 7 words. So what it ends up with is, the best thing about AI is its ability to learn from experience. It's not, and it will keep going because the model is doing its job, but we've told it to stop after 7 additional data points. Okay. Now, this is a different view of the same kind of idea, but it's put in a more mathematical context. So if we look closely at what we see here, you're looking at all of the ways that you can attach the word and determine the probability of how those fit together. Because it's not just what is the next word. What the models are doing in the background is it has already assigned a semantic meaning. And so it's not just what does the next word tell us, it's also what does the next set of words tell us. Where is this going? What is the overall semantic meaning of what we're asking for? And of course, that is a part of the transformer model. When we talk about this idea of what was proposed in the early paper, Transformers, attention is all you need. Some of the things that they plugged into the development in order to turn it into something like GPT-4 is they took this idea of, let me have the mathematics behind the models actually extrapolate forward and backward the entire meaning of the sentence. And so what we're seeing here is an illustration of not just a single word, but a continuation, so that we get a meaning by adding additional words. Now, Stephen took this a totally different direction, but I think it's actually really helpful. And there's kind of two ways that I see this probabilities on letters. And I'll come back to this at the end of the discussion as I'm closing out. But if we go back to the very early days of this concept of AI, you really can't avoid the historical references to Alan Turing. Now, if you're up on the Hollywood movies, you might have seen the movie that was released a few years ago called The Imitation Game, starring Benedict Cumberbatch playing the role of Alan Turing. And it was telling us the story of the deciphering of the Enigma code that was used by the German army in World War II to encrypt all of their communications. Now, there's some really startling scenes in that movie, and it is mostly true to the reality. I really enjoyed listening to Alan Turing's biography, but I'm a huge fan of Audible. I'd love to use it, but Alan Turing's biography was something on the order of 40 hours. So it's a pretty big commitment, but it did tell us in detail about Alan's life and many of his experiences. And one of the things that comes out of both the story told by the movie and the book is how Alan really understood this idea of cryptography and how at its core, you were translating one thing to another. And so if you could find a shortcut, a way to understand language, you might be able to narrow down the number of choices that were meaningful in creating the translations. Now, in the early days, they used something called a crib sheet that basically was an overlay to help you identify that unique set of information that might give you a hint to what the pairings of letter substitutions were in that Enigma device. This first chart here is showing us the repetition, the frequency, the likelihood or probability of the occurrence of a given letter from the alphabet, A through Z. So A is very common, but E is the most common. And so if you've studied anything about cryptographic text, one of the first things that the mathematicians key in on is that frequency of letter. Because if you're able to identify that one letter, if you've substituted, right, let's say that you've just slid the alphabet over a few characters, right? So if we took E and we substituted R, if you kept seeing R a lot, that might be an indication that you've just slid the alphabet over and done a direct substitution, because E is the most commonly occurring letter. Now, the visual that Stephen gives us here shows us, again, that you have a hot spot in a few places. But it's not just the occurrence of the letter, it is the occurrence of the letters together. And now you see that what we're beginning to move toward isn't just, I need to predict the next letter. I need to predict the next letter and the letter that goes after it. So it's not enough to predict simply the next value. You have to put them together in a meaningful way. And then this illustration here, this graph, is really a sort of behind the scenes for how the AI model is putting all of these numbers together. You have a series of numbers that come together to create a value, and that is the underlying mode of operation for the model. Now, this isn't something I'm very practiced at explaining, but essentially, you take these numbers and you put them together, driving toward a particular meaning, and it is the calculation of all of these values that allow the models to do what they do. And the best way that I have come to understand this concept is effectively taking the semantics of the phrases and the words and translating that into a number across many dimensions. You know, you and I are familiar with three-dimensional space. The fourth dimension is typically referred to as time, because you have to be positioned X, Y, and Z. And then if you add the time to that, I can be in this spot now, but in a different place later. So that can explain the temporal effects. If you take that concept of 4 dimensions and you scaled it up across many, many more, so many that we really don't have a way to illustrate it or draw it for you to see, you're starting to get an idea of what the neural networks and the nodes behind them might be building. And so this is the next layer that Stephen is trying to explain, how these data points come together to form a plane on the X and Y. And if we keep going, you can actually take that a little bit further. And I've got some other slides in here that I might come back to later, but we have this concept of a vector embedding, and we've been using this to augment the models with external databases. If you take a look at the vector embedding here, you can see that you've got a series of numbers. And so by collecting all of these numbers together, you can start to represent information in a more mathematical way. And that is the core of how these things function. It's just at a very, very incredibly large scale. And we don't need to understand where all of the points are, because the point of the model is it is taking all of that information and bringing it together in a way that can be leveraged in providing that answer. So when you ask it a question, it is using the conjunction of all of those bits of information to bring together and pull out the things that you need. Well, I'm not the first person to have proposed this. In fact, I borrowed this idea from someone else, and it's been so long since I've seen it. I'm honestly not sure where exactly I saw this thought expressed, but it's been something I've been thinking about a lot today as I was putting together my presentation this evening. I came across a tweet that was talking about someone that's a student that is working their way through the admission process, trying to get into the next level of education, and they needed a recommendation letter. And in requesting that recommendation letter, they actually sent a prompt of the essence of what the letter should say about them. Now, that was a seed for the person to write the letter. So they didn't write the letter for them, but they gave them a place to start from, because indeed they wanted to have the genuine reaction of the person. They didn't want to override their prevailing thought, but also provide a meaningful way to get started. And I started thinking about this idea, and there are so many things that we create to try to help communicate and explain things to other people. And what I have learned over the last 5 years in trying to communicate with high-level business people that are not technology jargon affiliated, how do you take an idea and turn that into something that they will understand and be able to include in how they are informing strategy and building plans and working with others to determine what the right next steps are? And the goal is to be as concise as possible. One of the challenges that we have in the AI space, a lot of times, if you go to a large language model and you're having a conversation, you're going to get a very lengthy response. And I think some of that is intentional behavior in how we've trained the models, but also it creates a problem because it causes the models to be more verbose than is really necessary in forming that response. And there are two downsides to that. The first is, if it's generating a lot of tokens, that not arbitrarily increases the cost of the API call in interacting with it. Now, if you're using ChatGPT, that's not a factor for you. But if you're someone like me that's building solutions, that token count does matter, because oftentimes you are being charged by the token, both input and output speaking. But we want it to be more concise, because that will help us to be more effective in communication. If you don't have to say as much, that's really valuable. And some of this goes back to the ideas in information theory. Claude Shannon wrote a paper many, many years ago about the maximum capacity of any medium to transmit information. And I love to talk about this stuff, and I probably need to do a deeper presentation on Claude Shannon a bit later, because he's one of my favorite characters in science and really did some incredible work at Bell Labs in the early days of developing all of this technology that we use today. But anyway, let me get back to the point. Being concise is incredibly valuable. I obviously failed at that in this discussion, but if we can think about LLMs differently, one of the different modes of understanding what LLMs have done for us is this concept of compression. Now, what do I mean by that? If you take the world's information and you train a model on all of the available information, I don't know what the most recent numbers are, but we are talking about so much information on the World Wide Web. We're adding an additional, petabyte per month, or it's something outrageous. It's an incomprehensible amount of digital information that is being added to the internet and these sources of information that are used to train models all the time. But once the model is trained, that model isn't the same size as all of the information that has been fed into it, because it is doing a mathematical extrapolation. Now, what does that mean for us? It means that as we are going forward into the future, we're going to see more and more AI on devices, because they'll be able to pack all of that information and put it into something the size of a phone. That's compression. In fact, so much of what we've worked on in technology has been, in the past, being able to fit as much information in as we can, because we've had limited resources, storage or memory or compute capacity. And today, we're actually able to build bigger and bigger machines to aggregate more and more information so that we can compress it more and more and be able to glean useful information from that. Going back to the citation I mentioned earlier around making the recommendation paper, what actually happened in that conversation, in my mind, is that the student was asking for a recommendation and provided a couple of sentences of prompt that led to probably nearly a full-page letter. So the question I want to pose today, as we're thinking about all of this, is how can we leverage these models to remove redundancy in terms of the way that we interact with the world? Because there is so much that we can do to improve the way that we communicate. And so not only can you learn from these models, but I think it's actually possible for us to take it to the next level and make things as simple as possible in the shortest possible way by leveraging the mechanisms built into the models, the information that they're trained on. Look, if you go back to what Alan Turing and the team figured out in deciphering that Enigma code, they found a shortcut, a compression that helped them to more quickly decipher the code. They did brute force it. The machine did have to work through all of the combinations. But before they gave it to the machine, they cut down the number of possibilities. And that's ultimately what made it possible. See, they took advantage of a pattern and they exploited it in order to make the solution search more concise. So the takeaway here is, I think we might be looking at a future where we have a shorthand, a shortcut, a more concise way to have a conversation, to talk about information. What if we're able to take these large language models and turn that into a condensed form of information that we can use with each other? One of the killer applications of generative AI today is the concept of giving it a huge batch of text and saying, summarize that for me. And it does a pretty good job. And I think that there's something more to that. How can we refine our conversation with each other and consolidate that? So instead of writing a 400-page book, we have a prompt book. that's a few sentences that actually leads us down the path to discovering what content will be written in the book. As I mentioned earlier in the use case, prompts that write letters. Let's think about taking concise to a whole new level. And so the idea I want to leave you with today as I close out the discussion is, what can we do differently? How can we use the large language model capabilities to compress things and be more effective in the way that we communicate, to be more efficient in the way that we share information? Perhaps having AI generate giant blobs of text isn't the future that we want for each other. So let's apply it in a different way and find ways to communicate more concisely with each other. And on that note, got it done in a half hour. I noticed a few of you are on with me today, and I want to thank you for interacting. If anybody has any questions before I close out the live discussion tonight, I'd love to hear from you. And look, if you're too shy to talk while you're on the call, that's perfectly fine. I would welcome your comments, your feedback, your interaction on social media across LinkedIn and YouTube and X. I really love doing this live because it suits my personality. I hope you're getting some value out of it. Let me know if you are, and if you have any questions or thoughts. I'm always looking for things to talk about. I enjoy doing this each and every week. I think I'm probably going to be a little later in the evening because I've got a day job now. I've got really amazing things happening, learning about all of the possibilities for generative AI at a great company called ServiceNow that I'm really excited to join up as a solutions consultant for AI. So exciting times ahead for me, but I have no intention of slowing down or ceasing what I'm doing here. I just have to make all of the rocks in the sand fit into the jar. So I'm really looking forward to continuing this. The newsletter's not going anywhere. We'll keep that on a monthly basis. And I look forward to seeing you on social media. Have a great weekend, and we'll see you next week. Go make some AI mistakes.